Hi, so now we're going to do a tutorial on how to simulate the Curie temperature using the Vampire software package. Okay, so essentially what we want to try and simulate here is the phase transition from a ferromagnetic state in a nickel system to the paramagnetic state where all the moments now are misaligned. So essentially we want to reproduce a graph something like this where we can plot the temperature dependence of the magnetization as a function of temperature. Okay, so in terms of Vampire and how that actually works, we have two main files that we need to generate in order to run a simulation. The first one is the input file, which essentially defines what kind of system you want to run, how big it is, for example, how many time steps you want to do, what kind of simulation you want to do, other parameters such as minimum temperatures, maximum temperatures, and so on. So this is kind of the control file that kind of tells Vampire what to do. The other file is the material file, which is a specific file for telling Vampire what magnetic properties your system has. So this can be simple. It could be a simple single element system, or it can be much more complicated. So for example, you can have something like magnetite with A and B sites, or you can have neodymium ion boron with, again, a range of different magnetic properties for different sites. So it can be more or less complicated, but here we're going to start with something quite simple, looking at elemental nickel. Okay, so as with all atomistic simulations, the first thing you have to do is determine the fundamental properties of your system before you run the simulation. So here we have a simplified spin Hamiltonian, which consists of only two parameters. Firstly, we have the usual Heisenberg exchange interaction, which then gives you a ferromagnetic ordering at low temperatures. And the second term is actually a uniaxial anisotropy. In reality, of course, nickel is actually cubic, but we just add this in for some kind of simple kind of approximation. It's not so important. I mean, in terms of the Curie temperature, the anisotropy is 1,000th or 10,000th of the energy. So essentially, it's unaffected by the size of the anisotropy unless it gets extremely large. Okay, so in terms of these files, since we've now defined what we want in terms of the spin Hamiltonian, we now have to define our various constants inside of that. So in the material file, which by convention is usually with a .mat file extension, it doesn't actually matter what it's called. You can include all the material properties for your system. So the first line that you have to include in any materials file is the number of materials that file contains. That essentially tells Vampire how many materials it is expecting to deal with. So in this case, the first one is material, number materials equals 1. So we only have a single type of magnetic atom in our system. Also note that anything with a hash in front of it is actually a comment. And so you can kind of format your file logically so that you can kind of recall where the different sections may be important, for example. Also, when I'm looking at new materials, I typically put in, say, references to academic papers or to books where I've got my kind of parameters from. It's very helpful if you want to go back in a year's time. So, oh, where did I actually get the parameters for this simulation from? If you can go back to the material file, say, okay, I got it from this particular paper. Okay, so in terms of the format for the material file, because we can have up to 100 different materials in our system, you can actually have a kind of array format. So here the material square bracket 1 indicates that this is the property for material 1 in the system. Similarly, for material square bracket 2 would be for the second material if you have them, and so on. Okay, so the first parameter here is material name, which is a generic name which can be any freeform text that you like. Spaces are not included, so typically you should not include spaces in that name, but it gives you a unique identifier for that system. It has no other meaning than a kind of a unique name that appears in the log file. So in this case we're doing nickel, so I've used the elemental name for nickel. The second parameter is then the Gilbert damping constant, which for this actual simulation we're not going to be using. But typically it's small for metallic systems, and so we set a value of 0.01. It's approximate, but Again, if you wanted to get a more accurate value, then you'd probably have to look into the literature and see what measured values there are for nickel. Okay, so in terms of the Curie temperature, then the next parameter is the most important one, which is the exchange interaction. So in Vampire, this is defined between two different types of atom or material. Because we only have one here, we only have an interaction between material 1 and atoms of material 1. So the second set of square brackets defines the material which you're kind of defining the interaction for. So in this case, material 1 interacts with atoms of material 1 with a constant of 2.757 times 10 to the minus 21 joules per link. So that's obviously derived from the mean field expression, including the correction for spin wave factor, and assumes an FCC lattice, where you have 12 nearest neighbors per spin. Okay. On the next line, we have then the atomic spin moment. So again, this is then the size of the local atomic moment in the system, which for experimental measurements is about 0.606 Bohr magnetons per spin. We have a new parameter here, which is the exclamation mark, and that gives you actually a unit value to a parameter that you define. So in this case, the units for atomic spin moment are μb's, which is Bohr magnetons. Vampire supports a range of different units, and we'll see some more of those a bit later. Okay, the next parameter is then the uniaxial anisotropy constant, which defines the strength of the anisotropy. In nickel, anisotropy is extremely weak anyway, so for atomistic simulations, typically it doesn't have much impact on the dynamics. So this is a very small energy. As you can see, it's 10,000 times smaller than the exchange energy. So a very, very small parameter. It has almost no bearing of the on the Curie temperature. The final parameter is then material-element. So this actually has no higher meaning than actually assigning a unique magnetic element to each atom type. So if you look at common magnetic viewers, structural viewers such as RASMOL or JMOL, then you'll see that different atoms have different colors so that you can identify which atoms are which. So this parameter does the same thing with the Vampire, that when you post-process the data to produce a crystal structure file that you can then view, then you can assign a different element to each material. It doesn't have any kind of physical meaning other than just assigning a different color to different atoms in the system. Obviously, for a single material, it's not particularly useful, but when you have complex crystal structures or different materials or core shell nanoparticles, it allows you to very easily inspect the different atoms and make sure that you're actually generating the system correctly. Okay, so in terms of the calculation, then we want to reproduce this figure on the right here, showing the temperature dependence of the magnetization. So I've already mentioned that we have essentially a spin Hamiltonian, which is dominated by the exchange interaction, where we extract our exchange constant from this mean field expression here. Okay, so one of the things when you're doing temperature-dependent calculations is, in fact, it takes a little while for the system to actually relax to an equilibrium state. So for example, say I had a system which is completely ferromagnetically ordered, like so, then if I suddenly increase the temperature, it actually takes a little bit of time for those spins to thermally fluctuate and to essentially reach a thermal equilibrium state. So in Vampire, this process is kind of accounted for by having two specific regions of simulation. The first one is an equilibration time, where you allow the system to essentially thermally evolve to reach a nice equilibrium state. And then you have a second period of time where you then calculate statistical averages for that thermodynamically equilibrium state. So depending on the integration scheme that you use, and whether it's Monte Carlo and what kind of Monte Carlo moves you use, you will have to use a different number of equilibration steps to get to thermal equilibrium. Typically a good number is at least 1,000, ideally 10,000, 100,000 equilibration Monte Carlo steps would guarantee pretty much that you've got an equilibrium state as your starting point. Obviously, computational time increases significantly as you increase the number of equilibration steps, and so it's some compromise between how accurate do you want your simulation and how much computational time you have available. Okay, so in terms of Vampire then, we define two different time parameters. The first one is equilibration time steps, which is the number of time steps done in this equilibration phase. And then secondly, we have a loop time steps, which then calculates a number of averaging steps where you calculate the parameters over time. In this graph here, you can see actually that the magnetization then relaxes in sort of exponential form. So it starts in a very ordered state, and then we increase the temperature actually to quite a high temperature. And so the system has far to go in terms of equilibrium, so it takes several thousand steps to actually reach that, at which point then you can perform your averaging. If you do smaller temperature steps and increments, then the time needed to, or number of time steps needed to reach equilibrium is proportionately less. Okay, so essentially that's what we need to do then. We need to then loop over multiple different temperatures and generate an average magnetization for each temperature. So now we're going to set up the input file that will allow Vampire to do this calculation. Okay, so this is a bit long, so quite a few parameters in here, so we'll kind of go through step by step. As with the material file, hash is a comment, so it allows you to structure your input file so that you can kind of put different parameters in different places, but have some order for it. Typically what I do when I do a new simulation is have kind of a default one I start with, and then I then modify that as I need to actually do the simulation I want to do. Okay, so the first thing we're going to look at is creation attributes, which essentially sets up the basic properties of the system. So the first line here is create crystal structure, which equals FCC, which is short for face-centered cubic. Vampire actually supports a range of different crystal structures, so simple cubic, body-centered cubic, face-centered cubic, hexagonal close-packed as the kind of basic single material ones. There are also new materials such as rock salt and spinel, which allows you to generate more complex systems that are built in. So obviously the number of neighbors change depending on the crystal structure. So for example, if it's simple cubic, you have 6 nearest neighbors. If you have a body-centered crystal, it's 8 nearest neighbors. Or for FCC and HCP crystals, you have 12 nearest neighbors. And so the exchange constant that you need, if you're using the mean field formula, will vary depending on how many nearest neighbors that you have. Okay, so this essentially then creates a bulk crystal of FCC, in FCC order, so that you can then generate your system from that. Second set of parameters are periodic boundary conditions. So here we want to eliminate surface effects. So if you imagine if I had a cube of nickel that's of a small size, say a few nanometers, then obviously at the boundaries you have missing exchange bonds with where there would normally be atoms. So what periodic boundary conditions does is say, if I have an atom on the edge, it wraps it round so it then interacts with the atom on the other side. And I apply these in X, Y, and Z directions. So essentially it removes those surface atoms that would otherwise be there. There's still a small finite size effect because you have a finite number of atoms, but what we're doing here is eliminating the surface effect. So they're kind of two different, subtly different effects to take into account. Okay, in the next section then we have system dimensions. So this sets up fundamental properties. So for example, the size of the unit cell. So here it's set to 3.524 angstroms, which is then typical for nickel. And here we're simulating a relatively small system of 4 nanometers cubed. So we define our system size in X, Y, and Z direction as 4 nanometers. You notice here also we have some new units. So capital A is short for angstroms in the dimensions, and nm is short for nanometers. So you can define actually a range of different units within Vampire to make it easier to kind of figure out how big things are. So I typically use these dimensions as that's what's found in literature. Okay, the next step is then to load in the material file. So here we have the material file equals ni.mat. So this will then read the material file in the same directory and load those properties into Vampire then. So it essentially reads that separate file. And this is essential if you want to actually load in those material properties. Okay, So that defines the kind of fundamental setup of our system, what crystal structure, how big it is, and what material properties that we want. We can then move on to simulation attributes. So this then tells you the kind of range of temperatures we want to, say, loop over, how many time steps you use, and so on. Okay, so because we're doing a loop over temperature, which is actually built into Vampire already, we can simply define a minimum temperature and a maximum temperature. And this defines the range of our temperatures that we're going to kind of loop over. And we can also define an increment, which in this case is 25 Kelvin, so that we do that in steps of 25 Kelvin. So the first simulation will do 0 Kelvin, then we'll do another simulation at 25 Kelvin, then 50 and 75 and so on, all the way up to 800. Yeah. Obviously, if you want to have more precise results, then you might do smaller increments, maybe 10 Kelvin for publications, and also typically a larger simulation than 4 nanometers. The finite size effect for 4 nanometers is quite large. Okay. The next parameter is the time steps increment, which is essentially how many time steps you take between taking statistical samples. Because of the efficiency of the Monte Carlo algorithm, actually here in Vampire we typically use an increment of 1. So actually we sample every single sample generated by the system, because our acceptance rate is typically around about 50%. And so the correlation between one state and another state is actually quite low, and so then we can take adjacent statistical samples and still get good statistics of the system. If you want to be a little bit more careful, then you could make increment maybe 2, 3, 5, depending, and that will then kind of reduce the sampling rate, so your statistics will be worse, but you will have more statistically independent samples. So there's a kind of a balance in terms of the number of steps that you want to make and the quality of the statistics that you generate. But in our experience, we have not seen any problems with correlations with it so far. Okay, so now we have to define the two regions of simulation for each temperature. So firstly, the number of equilibration steps that we take before we start the averaging calculation, and then the number of loop time steps that we then want to take to actually average the magnetization in the system. So in this case, we want to make the simulation quick, and so we set both to 1,000 steps. It's not amazing in terms of statistical averaging, but it allows you to make a good approximation in terms of how the system will behave. In production, I would probably make these 10,000 each to give a better kind of idea of a good average and very smooth data. In the next step, we want to define our program and integrator details, so we know which simulation we want to run, and also which integrator we're going to use. So because here we want to do a Curie temperature simulation, we can use the Curie temperature program within Vampire to actually automate the looping of the temperature and also this equilibration period and then averaging period. So we can use the standard Curie temperature simulation in Vampire. We also define a Monte Carlo integrator to essentially deal with the temperature or time step evolution of our system. The default in Vampire is now the adaptive Monte Carlo algorithm, which gives you a kind of acceptance rate of 50% independent of temperature and configuration details. So it's a very efficient Monte Carlo solver that will reach equilibrium very, very quickly. Typically, actually, a few hundred steps is sufficient. Okay. To this point, actually, all of these parameters in the input file are free format. So it doesn't matter which order you put the parameters in. You can arrange them how you like. It doesn't matter which order things appear in. I just do this way because it's kind of a logical way of doing it, but you can actually order them any way you like. If you have the same parameter twice in the input file, then actually it will overwrite that value with the new value. So it won't tell you, oh, this is in twice. It will just use the latest value in the files. The exception to this is the data output section, where this defines how data is outputted into the output file. So you first define what data you want and also in which order it is to appear in the output file. So here we want to have some output. So for example, we output the real time, which is the time steps times by the time step. By default, this is actually 1 femtosecond. Of course, for Monte Carlo simulations, in reality, real time doesn't have any meaning. So it's just kind of a substitute for time steps. We also output the temperature as a function of time so that we can then correlate our magnetization calculations to the temperatures that were used for that portion of the calculation. And we also output the magnetization as a function of time and also the magnetization length as a function of time. So these are the instantaneous values at the point where you output the data. So by default, this is actually after every single temperature loop, then it outputs the final magnetization and the final magnetization length. And the final output we want is the mean magnetization length, which then performs an actual average over the loop part of the simulation. So this is this value actually that we want to plot in the end. This is our kind of average magnetization at each temperature, which we then plot as a function of temperature. Okay, so with that, we can then go and simulate the Curie temperature of the system. Okay, so here I've prepared the input files already. So if I list what's in here, I have a nickel.mat and an input file, and also results from a previous simulation, but that's fine. Okay, so the cat command is quite useful if you want to just display files in the terminal, and tab also gives you autocomplete, which is useful if you want to just kind of finish off a command when you don't want to type the whole file name. So this just prints out, for example, the input file to screen. So here we have the material file for nickel, and similarly for the input file, we can do the same, which gives you then the kind of parameters used here. Okay. I've also, in this case, added two new parameters to the input file. Here, I want to print the temperature to the screen and also the mean magnetization length to the screen, so you can see actually how the calculation is progressing. For these kinds of calculations, this is fine because you only have a few data points relative to the number of calculation steps that you make. On the other hand, if you're doing maybe a 100 nanosecond simulation, then you will output lots of data to screen, which is extremely inefficient and will slow down the calculation. So only use the screen output if you're maybe testing or doing something that's computationally inexpensive in terms of the number of outputs that you make. Otherwise, you will slow down your simulation significantly. Okay, so now we can go and run the simulation. So to run Vampire, I've installed that in my home directory. So on the Unix system, that's typically tilde/Vampire. And then I'll bring up the Vampire serial command. So this will run the serial version of the code to execute this Monte Carlo simulation. So here the simulations are progressing. You can see that the temperature is printed out here as well as the mean magnetization for each temperature. And as the simulation progresses, you can see that the magnetization decreases at first relatively slowly. So you get 2% or so decrease with temperature. As you get to higher temperatures, you see that the actual magnetization decreases more rapidly. So this is the kind of characteristic of the fact that the magnetization is kind of cell-correlated in the sense that it preserves order, but as you get to higher fluctuations, then that kind of correlation effect starts to weaken, and so the magnetization drops faster as you increase the temperature. You can also see with Vampire that it prints out the number of atoms, for example, and so the information at the beginning, so you can kind of check that is this roughly the right size, and also if it's more than a few thousand atoms, then if you're not using a parallel simulation, it may take some time to do this kind of calculation. Okay, so that's the calculation completed. It tells you actually how long the simulation has taken, so about 84 seconds in total. And also calculating how many Monte Carlo moves have been made, as well as the acceptance rate. So because we use this adaptive algorithm, it's very, very close to 50% by design. Okay, so now we have two new files in the output. We have a log file, which gives you a kind of a record of the simulation and what was done. So I can just kind of show that briefly. And if I scroll back up, so it basically says some useful information, for example, like where the simulation has been run, which version of Vampire was used, and a specific Git hash which tells you precisely which version of Vampire was used for that calculation. and then some various sort of setup things, and then finally some information about the simulation as well. We also have the output file, so for cat output. So this has quite a few lines, but again includes some basic information at the top, where the simulation was run and when. So if, for example, you run it on some system and you're not sure where, as long as you have this header file, you should be able to find out where this was run on, say, a different system and when. So we also have our data here. So the first column here is the time step, or time. So because the default was 1 femtosecond, then it now correlates to some number of femtoseconds, but in reality this is more like time steps. The second column, as we defined, is now the system temperature, which now goes from 0 to 800 in steps of 25, as we defined. We then have a different number of magnetization measurements. So these are the first 4 columns here represent the instantaneous magnetization of the entire system. So we have X, Y, and Z components, which are unit vectors, tells you that basically it's starting along the Z direction. And then also the average magnetization at that point in time. This is the same actually as the next column along, which again is the magnetization length. Again, the instantaneous one at that period of time. And then finally, our last column is the average magnetization taken over the entire simulation. Okay, so now that we have our data, we can now plot that to see whether we got the right answers. So for that, we start with the GNU plot program. So type GNU plot and then enter. This is an interactive program which allows you to plot various things and also do fitting. So here we want to plot the magnetization, or the mean magnetization, as a function of temperature. So we can use P, which is short for plot. We define the output file name, which is in this case output in double quotes. U, which is short for using, and then we define columns. So we want the second column with the 8th column, which should plot our data. And finally, you want to plot that with points. Okay, and that gives you data like so. I'll just make that a little bigger. So you can see here then we have a temperature-dependent magnetization, which is linear to start with, and then decreases more rapidly as you approach the Curie temperature. And it's around about 650 Kelvin, which is what you would expect for nickel. Okay, so that's fine. We have that. Can we kind of fit that to extract out the Curie temperature more precisely? Of course, yes. So we can define a fitting function here that will then fit our data and allow us to calculate that. So we can define a function in GNU plot as m of x equals. I'm going to use a special ternary operator, which is basically a split function, so that for one half of the fit we can do one equation, for another half we can do another equation. So if x is less than tc, then we want to plot 1 minus x over tc all to the power beta. If it's greater than tc, then we want it to be 0. Okay, so this defines our kind of split function. We need to define our fitting parameters. So tc is approximately 650, but we'll start at 600 to start with. And beta we'll set at 0.4. Okay, so now we've defined our fitting function and our initial parameters, so we can now fit that to our data. So we can do fit m of x to, again, output using columns 2 and 8. Now we use the var command to say which parameters we want to vary. So in this case, tc and beta. So we enter that. That will then go and fit the data to that equation. Okay, so great. So that's fitted well. We got a few percent error, which is good. So it means our fit is sensible. So we can now plot all that together. So if we go use the up key, you can recall previous commands that you've used. So we can plot now our data, but also our function m of x with lines, which then fits rather beautifully as so. And here the extracted then fit that we get is 635 Kelvin, which is a little bit low, but again we have a slightly small system, and so you expect that actually the Curie temperature is maybe a little bit lower than the bulk. Okay. Okay, so essentially then we've reproduced this calculation. When we now have a graph of m versus t, and we're using this fitting equation here, m of t, which fits the classical model extremely well. So it allows you to extract the Curie temperature and also the critical exponent beta, which is essentially how rapidly your system magnetization varies with temperature. It defines, if you like, the shape of the magnetization curve.